Hello guys, welcome back to Foolish Engineers videos. Have you ever noticed the whole world is very bullish on renewable energy like wind energy and solar energy. Many countries like India and China are also heavily investing in these technologies. Out of those, solar energy is considered more efficient and easy to use. Today, we are going to see what kind of electronics goes behind it, and if you watch till the end, there's something amazing that I want to share with you. So, stick around. Before going into the concepts, I would like to mention today's sponsors. This video is made possible because of Texas Instruments. They are pioneers of semiconductor world. They make those tiny ICs which we see in the circuit boards. We'll see more about it at the end of the video. We already know using solar panels, we can convert solar energy into electrical energy. We can simply install these solar panels on the roof of our home and theoretically we'll get unlimited renewable energy. We use multiple small solar panels to create a full setup on the roof. But it is not that straightforward. There are many challenges to it. Very first is that the solar panels generate DC power and our home appliances work on AC supply which you get from the grid. And the voltage generated by these solar panels is never constant. It depends on the sun's light and heat. So this parameter is never constant throughout the day. Well, to mitigate all of these problems, we have to take the help of power electronics, which will provide maximum power out of these solar panels and convert this DC power into AC. For this job, we use different type of inverters, which are called solar inverters. Solar inverter converts DC power into smooth AC so that we can use our appliances at home easily. Also, it tracks maximum power which can be extracted from the solar panels. And if there is excessive energy, we can give it back to the electrical grid so that we can earn more money from the setup. It requires complex hardware and power electronics logic. So, a normal circuit first converts this unregulated DC voltage into constant DC using a DC to DC converter, which we have seen in many of our older videos. Once we get DC, then it converts this DC supply into AC power using an inverter. There are many different setups on how these panels and inverters work together. But in this video, we'll see bidirectional micro inverter based setup. In this setup, we connect a DC to DC converter to each solar panel which will provide constant DC and maximum power out of this solar panel. We stack all of these units together and give it to a common inverter which converts DC power into AC. Now, this is how the inverter circuit looks like. There are so many components and it looks a bit complicated as well. Let's make it easy and divide them into smaller blocks. First, we have solar cells. Let's consider it produces voltage between 30 volts to 60 volts DC, and this will get converted into constant 75 volts DC. And there will be multiple solar panels and DC to DC converter which are stacked together. Now, we cannot directly convert this DC power into AC supply. So here we will do one more DC to DC converter which will convert this 75 volts DC to 400 volts. The main advantage of this part is to give higher voltage for AC conversion and provide isolation between input and output. Next block is the real inverter and it converts 400 volts DC into 230 volts AC power which powers our household appliances. Let's name these blocks A, B and C. This circuit is a bidirectional converter which flows the power in both directions. For example, instead of solar panels, we can simply connect battery packs to store charge from the grid. Here, this block can convert 230 volts AC to 400 volt DC using the same inverter circuit. Then this stage can convert 400 volts to 75 volts DC from the DC to DC converter stage. And finally, this block can convert 75 volts DC into lower voltages if needed. The first block, which converts unregulated DC into regulated one, is a DC to DC converter block. As you can see, the input voltage might be around 30 volts to 60 volts DC, and we want to convert it into 75 volts DC. So a simple non-isolated DC to DC converter will be sufficient here. So we'll use synchronous boost converter for each solar panel. Apart from converting the DC voltage, this block gives efficient output from each panel using maximum power point tracking algorithm for solar panels. So it consists of mainly two FETs, an inductor, voltage and current source for feedback control circuitry, etc. So if the power transfers from block A to B, it works as a boost converter which steps up the voltage using this configuration. And when the power transfers from B to A, this block will work as synchronous buck converter using this configuration. And it will simply step down the voltage. Next is block B, which is a high power isolated soft switching DC to DC converter. In this circuit, there is a CLLC converter, which converts 75 volts DC to 400 volts DC using full bridge configuration on this side and a half bridge rectifier on the other side, with a transformer in between, which provides galvanic isolation between solar cells and the grid. So if there is any short circuit on either side, the other side will not get affected. Just like block A, this is also a bidirectional DC to DC converter, which can convert 75 volts to 400 volts and 400 volts to 75 volts depending on the flow of current. It provides good efficiency and handles high power easily because of this CLLC converter, which gives zero voltage switching. We have already seen these terms like zero voltage switching and soft switching in the older videos. You can click here to check more about it. Usually there are so many A blocks stacked together as input for this block B, so it should handle high power. Now finally comes the block C, which converts DC 400 volts into 230 volts using inverter circuit. This is also a bidirectional converter which can convert 230 volts AC into 400 volts DC when the current is flowing in this direction. By now you might have understood that the solar inverter is not that easy. There are so many complicated power electronic circuits going inside. Well, that's just a start. The main challenges for this are to get this converter to work in harmony with each other. Also, taking care of the bidirectional high power with accurate logic and minimizing the electromagnetic noise in this converter. And we have to do all of that by making this circuit smaller and more importantly very efficient. Look at these FETs. There are at least 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11 FETs in this circuit. If there are more A blocks, then the total number of FETs will also increase, and most of the problems like electromagnetic noise and power loss occur at these FETs only. So being a power electronics engineer, we have to select these FETs very carefully because they are real muscle behind the circuit, and with that we also have to take care of how to drive these FETs efficiently. I'm not even coming to this logic circuit. That's a different world itself. For now, we'll focus on this part. To make sure that this circuit works efficiently, we have to select a good set of FETs with optimum performance. We have also seen many basic things about these transistors in older videos. If we really want to know how to make efficient solar inverter, we should follow the latest technology trends. And not just FETs, we should select accurate gate driver circuits for these FETs as well, which will switch them very efficiently by producing minimal power losses. Well, it is a hard job, but there are a few application specific ICs which offer latest technology. For example, look at this semiconductor called LMG2100 R044 GaN power stage with built-in gate driver. From the name only, you can detect that it is a GaN FET, which is the latest technology. And it doesn't have just one FET. It is an H bridge consists of 200 volt 4.4 milliohm GaN FETs. On top of that, it has an internal gate driver which takes care of this MOSFETs. So we don't have to worry about gate path, charging, discharging of the gate capacitor, and gate resistor. Everything is covered inside. This IC can be used in this block A for DC to DC converter, and it has the smallest packet size compared to similar devices which offer the same power capability. You can check about this and more GaN fed power devices like this on TI's website. That's not the only thing. What if I tell you that I'm going to witness these similar new technologies for other blocks as well and many other applications in a few days at Texas Instruments booth at PCIM Europe 2024 in Nuremberg, Germany. It is an international event for all power electronics engineers who want to know about latest trends in this industry. I would really like to invite all of you to this event and experience this journey with me. Of course, you have to pay your ticket. Well, that's all for this video. I hope you picked up something useful from this. The reference of this design is added in the description below. While checking the reference, don't forget to hit that subscribe button as well. It's right over there. I'll see you in PCIM 2024. Till then, stay hungry, stay foolish,